2.5 Covariant derivatives. 2.5.1 The covariant derivative. Let's review the covariant derivative operator as described by Wald, with additional discussion regarding the algebraic topology induced by having a consistent chain rule. The derivative operator is defined to satisfy 6 conditions: linearity, Leibniz rule, commutativity with contraction, consistency with directional derivatives on scalar fields, torsion-free chain rule, imposed at alg top level, on tangent space mappings, see Appendix B. Any two derivative operations must agree in their action on scalar fields from 4. See equation 2-41.
At P, gradient tilde sub A W sub B times and gradient sub A W sub B depend on how W sub B changes as one morays away from P. However, gradient tilde sub A W sub B minus gradient sub A W sub B depends on W sub B only at P in this regard. Suppose W sub B prime equals W sub B at P. We can write W sub B prime minus W sub B in terms of a collection of functions that vanish at P, f sub alpha, summed according to independent decomponent scalar factors mu sub B raised to the alpha power. Eventually they sum to a d-dim vector. See equation 2-42. At P we can then write. See equation 2-43. Where equality with 0 follows due to the mu sub B raised to the alpha power terms being scalars. Thus we have. See equation 2-44. For arbitrary W sub B prime, thus, gradient tilde sub A W sub B minus gradient sub A W sub B depends only on the value at a given point.
Since gradient tilde sub A negative gradient sub A times W sub B only depends on the value at a point, it defines a map on dual vectors at P to 0, 2 tensors at P, and it is linear, thus it must be a tensor of type 1, 2 at P, denoted C sub AB to the C power. Gradient sub A W sub B equals gradient tilde sub A W sub B minus C sub AB to the C power times W sub C, and times C sub AB to the C power equals C sub BA to the C power. Equation 2-45. Now, see equation 2-46. Since the contraction is a scalar. In turn, this then indicates that. See equation 2-47. Generalizing. See equation 2-48. Now consider a metric with compatible derivative operator. See equation 2-49.
Note that G sub BC is the metric compatible with the other derivative operator, gradient sub A. So let's do a notation change and also introduce a one-parameter, line function mapping, parameterization. So, let's sub to the lambda power gradient sub A denote the operator associated with G sub A B of lambda, and let's sub to the O power gradient sub A denote the operator associated with sub to the O power G sub A B, for which the associated C sub A B to the C power of 0 equals 0, but for lambda is not equal to 0 we now have. See equation 2-50. Recall that. See the equation. So, see the next equation. And using. See the equation shown. And.
See the equation. We get. See the equations shown. Thus. See equation 2-51. See equation 2-52. If sub to the 0 power G sub AC is a solution of the vacuum Einstein equation, then sub to the 0 power R sub AC equals 0. However, in the analysis this simply provides us with a convenient reference configuration. With such a reference configuration,
see equation 2-53. If we define, see equation 2-54. Then, see equation 2-55. Thus, see equation 2-56. So, dropping the OO superscript, this simplifies to.
See equation 2-57. This will be useful in sector 3.2.2. Example 2.1. Show that any two covariant derivatives, gradient sub A and gradient tilde sub A differ by a tensor C sub CA to the B power. See the next equation. With C symmetric on its covariant indices. C sub CA to the B power equals C sub AC to the B power. Use abstract indices. Then, use Leibniz to show the analogous formula holds for any tensor. See the equation shown. Solution. Consider gradient sub A negative gradient tilde sub A times V to the C power W sub C since a covariant derivative is a map between the 2 by 1 column matrix Mn and the 2 by 1 column matrix Nm tensor fields which satisfies, among other things, gradient sub AF equals G of our AD times F for scalars. Then, since V to the C power W sub C is a scalar, we have gradient sub a negative gradient tilde sub A times V to the C power W sub C equals 0. Now, using Leibniz, see the equation.
Thus we find that gradient sub a negative gradient tilde sub A defines a map of the one form W sub C to the 2 by 1 column matrix 0, 2 tensor. Furthermore, the map is linear. Consequently, gradient sub a negative gradient tilde sub A must be a tensor of type the 2 by 1 column matrix 1, 2, as this is the type which maps one forms to the 2 by 1 column matrix 0, 2 tensors. Denote the tensor field by negative C sub A C to the D power. See the next equation. C sub A C to the D power is also symmetric on its covariant indices, as can be shown by considering W sub C gradient sub CF. See the equation shown, which is symmetric on A and C. So, see the equation. And gradient sub a negative gradient tilde sub A times V to the B power equals C sub CA to the B power V to the C power. So C sub CA to the B power equals C sub AC to the B power.
Now, individually the covariant derivatives satisfy Leibniz rule, as will any linear combination of them. So, the application of gradient sub a negative gradient tilde sub A to any tensor can be expressed in terms of its action on the vector and dual spaces of the tensor product space. Thus, for contravariant indices we get a contraction as with a dual vector. Gradient sub a negative gradient tilde sub A times W sub C equals negative C sub AC to the D power W sub D, while for covariant indices we get that of a vector. Gradient sub a negative gradient tilde sub A times V to the B power equals C sub CA to the B power V to the C power. Thus, see the next equation. 2.5.2 Riemann tensor. Let's rederive the Riemann tensor by way of the Cartan structure equations. A complete description of the method is given in Chapter 4, using abstract indices. The Riemann tensor is defined as follows. See equation 2-58. Using an orthonormal frame and Cartan's formalism. See equation 2-59. See equation 2-60.
Cartan structure equations, using the notation omega to the I power dual basis vectors and open bracket U, V close bracket to the I power equals U to the J power the partial derivative of and denominator partial differential x to the J power V to the I power minus V to the J power the fraction with numerator partial differential U to the I power with respect to x to the J power. And have the I power of omega of E sub k equals delta sub k to the I power equals a constant for an orthonormal frame. See the equations shown. Thus, see equation 2-61. If we next define connection forms, omega sub j to the I power equals gamma sub jk to the I power omega to the k power, we expect omega sub ij equals negative omega sub ji in an orthonormal frame, or any frame where the metric has constant components. Let's show this. Start with. See the equation shown. Now have.
See the equation. Notice that. See the next equation. Consider. See the equation shown. So, see the equation. And we can now write.
See equation 2-62. Recall. See the next equation. Where we have. See the equation shown. And. See the equation. So, in an orthonormal basis, or one where the metric is constant.
See equation 2-63. Since the Ricci tensor. See equation 2-64. Implying. See equation 2-65. Note that. See the next equation. Will be useful in what follows. We have.
See the equations shown. Equals E sub k of gamma sub j script L to the I power minus E subscript L of gamma sub jk to the I power minus gamma sub jm to the I power gamma subscript Lk to the m power plus gamma sub jm to the I power gamma sub k script L to the m power equals E sub k of gamma sub j script L to the I power minus E subscript L of gamma sub jk to the I power. plus 2 gamma sub jm to the I power gamma sub open bracket k script l script close bracket to the m power. Thus, see equation 2-66. We also have, see the equation shown. Thus, see equation 2-67. Since,
see equation 2-68. We have, see equation 2-69, which is the Riemann tensor. Example 2.2. Show that gamma sub open bracket jk close bracket to the I power equals -1/2 c sub jk to the I power. Solution. We have e sub k to the power gradient sub a e sub j to the b power equals gamma sub jk to the I power e sub I to the b power, so see the equation. Thus, see the next equation. Example 2.3. Use the previous relation and gradient sub a g sub bc equals 0 to show that.
See the equation shown. Solution. See the equation. And we have.
See the equations shown. So,
see the next equation. Example 2.4. Prove the Gauss-Codacci equation. See the equation shown. Solution. A tensor over the tangent space of the 3 surface at a given point P is simply. See the equation. Where H sub AB is the spatial metric associated with a spacetime metric G sub AB induced by the choice of foliation sum from T to T to the a power a vector field on the manifold for which T to the a power gradient sub AT equals 1, T the global time function that labels sum from T to. Denote d sub kt sub c dot dot d dot raised to the a dot dot b dot power equals h sub e to the a power dot dot h dot sub f to the b power of h sub c raised to the g power dot dot h dot sub d to the j power of h sub k to the n power gradient sub nt sub g dot dot j dot raised to the e dot dot f dot power. Then, see the next equation.
Now we project out what is meant by d sub a d sub b w sub c. See the equations shown. Thus, see the equations shown. Thus, see the equation shown. And we get,
see the equations shown. H sub a raised to the f power of h sub b raised to the g power gradient sub f h sub g to the t power equals h sub a raised to the f power of gradient sub f n sub b, n to the d power plus h sub a raised to the f power of n sub b d to the t power times 1/2 gradient sub f, n raised to the g power n sub g, equals h sub a raised to the f power gradient sub f n sub b, times n to the d power equals k sub a b n to the d power. So, see the equations shown. Now, see the equation. So, see the next equation. And,
see the equation shown. Since w sub g is on sigma. Thus, see the equation. In a given coordinate system we thus have sub raised to the 3 power r sub alpha beta gamma delta equals h sub alpha raised to the exponent alpha prime and exponent of h sub beta raised to the exponent beta prime and exponent of h sub gamma raised to the exponent gamma prime and exponent of h sub delta raised to the exponent delta prime and exponent of r sub alpha prime beta prime gamma prime delta prime plus k sub alpha delta k sub beta. Gamma minus k sub alpha gamma k sub beta delta. Example 2.5. Show that. See the equations shown. And see the next equation. Solution. We have.
See the equation shown. Where r equals the athb power of g of r sub ab we have r equals g raised to the ab power of r sub ab plus the athb power of g of r sub ab, thus. See the equation. Using this in. See the next equation. We get. See the equation shown. Thus.
See the equation. And we have the desired. See the next equation.